So today we are fortunate to have Shazia to talk about supervised learning and semi-supervised learning. So Shazia is affiliated at the Vector Institute and also a machine learning engineer at Altis Labs. All right. So without further ado, let's give it to Shazia.
Okay. Well, thank you very much for that introduction. So, welcome to the first practical session on Learning Without Labels, the premium workshop. So just to give you another run through, which you probably heard about 3 times now. So this workshop is split kind of mostly working on unsupervised learning, and then the last week 3, will be on weekly semi-supervised learning. So I'll go through quite a few techniques on the last week, but by then you'll be really comfortable in what we're looking at and models and Pytorch. So then you'll really be able to ramp up the speed and pick up materials like there's no tomorrow. So I'm assuming all of you, or hopefully most of you at least, have looked at the lecture that already went out. And so it was a 1-hour lecture on unsupervised learning techniques. If you had burning questions whilst you were going through that material and you saved them for now, please feel free to send them in, let someone know, let your TAs know if you have questions as well, and hopefully they'll be able to answer them. But I thought today I would just give a very quick recap. So I can't go through all 50 slides, but I have the slides on standby if someone wants to go through a particular slide. But just to recap, I did go through certain techniques, certain situations whereby gathering labels is either just not doable whatsoever, or you can only get some labels and not all of them, where you have to sacrifice quality when you're gathering labels as well. So I mentioned one particular, actually a couple of particular projects that I've worked in the field of medicine, where the knowledge is really expensive, and actually getting clinicians to sit down and annotate them is also very expensive and subjective. I talked about anomaly detection, where it's not possible to really gather every possible scenario, so you need to, cut a threshold at certain scenarios you can model and have a model that can adapt and adjust accordingly. And obviously the last picture here is just a reminder that we're all human beings. We don't always agree, and that some of our decisions are not binary. They're not yes, no. And it's important to take that into account when we are building models as well. So unsupervised learning in particular, I mentioned why unsupervised instances can help, and this is a really nice picture of how, even though you don't know where all the reds and blues are, the fact that you know where they are in this high dimensional space actually helps you create that decision boundary, so that dotted line there. So using unlabeled data is usually helpful. In very few cases that not helpful. I also ran through deep embedding techniques, so the ability to take a very large data and embedding it into a compressed hidden dimension or latent space, or data embedded space. And we looked at autoencoders specifically. I'm not going to go through all of it, but if you have questions, have them come in. And then we moved on to generative models, and we were looking at, okay, autoencoders are great, but essentially they're a mapping function, so they're free to roam and adjust accordingly, which doesn't necessarily mean it's doing something clever. It just means it's adjusting weights to maximize its reward and maximize that reconstruction. And so we looked at generative models as another way of modeling your data in a more intelligent manner. And we looked at variation autoencoders in particular. And hopefully I went through sufficient detail in the lecture itself so that you can go away and implement this, because this is what we're going to be doing today. I'll come back to this. And I also described the loss function, which you will also be implementing today, also known as elbow. And after that, I kind of talked about this term called disentanglement. And I talked about this particular GIF during the lecture, but I didn't have it on hand. So here it is. It's a sphere in the cube. And the idea here, the colors are supposed to kind of indicate how independent they are from the background and the floor. So you should be able to elongate that circle, and the background and the floor should stay the same because they're independent of one another. So this is actually a really nice GitHub repo, which has a few of these GIFs where it shows when disentangle features don't work and why it's an issue. So feel free to check it out. And lastly, I kind of finished on a very quick overview of GANs, but I'm aware a lot of you have already used it in practice. So that hopefully this looks very familiar to you. And it's an idea of generating fake or synthetic data and complementing it with actual real data in order to build a model that's very strong and is able to build realistic images that mimic your training set. So that's a very quick 5-10 minute overview of what I went through. So are there questions based on all the content that I went over in the 1 hour? Yes?
Could you explain a little bit more about the generative modeling? How do you, what are exactly the inputs to the Gaussian distributions that are stuck in the middle and how they work?
Sure. So the question was, can I just go into the generative modeling and what the input and what the sampling here is. So the input is obviously our raw data, and I'm sure you know that. So in the sampling layer in the middle here, the input to it, I guess, after you've gone through your series of layers and you've built your abstract features and you've captured all the complexity and the patterns within that encoder component, it then goes into actually two sets of neurons. One is the mean, is supposed to represent the mean of your Gaussian units, and one is supposed to represent the variance of those Gaussian units. So they'll all be interconnected, although I don't show all the connections here. There's just two sets of them, and they're all interconnected in one layer. So it's actually a fairly big cyan blue layer there. And then once you've modeled that, and as the weights are updated during the training phase, what's supposed to happen is the mean and variance of those Gaussian units are supposed to adapt and change so that they're modeling your data sufficiently. And then when it comes to inference, you're sampling from that unit Gaussians. So based on that mean and that variance, you'll sample something from there, and then that goes through your decoder. And obviously during training, it goes through the loss function, which updates all the weights. So the input is your unit Gaussians, and the output from that latent space is a sampled set from your unit Gaussians.
Is there any particular sampling technique used there, or?
That's a good question. Usually we just use a standard sampling technique, but I don't know if anyone's used adaptations on that standard sampling technique. It's a good question. I'll have to look that up during the break.
Clarification. So the size of the layers,
yes,
dimension should not be equal, right? Because I can draw as many samples. I don't need to draw two samples from each distribution, one for the mean, one for the variance.
No, you'll sample from all of the unit Gaussians at the same time, and then that'll be passed on.
I can take as many samples as I need. Do I compute means and variances directly?
No, that they're all initialized randomly. They should settle through the loss function itself.
I mean, in the gap between encoder?
Yes.
So I have my means and variances defined as the last layer of the encoder.
Yes.
Then I have my distributions and I can draw samples.
You can draw samples from them.
Do I draw random samples, say, I don't know, k out of each? Then I compute means and variances and feed them to the decoder? Or do I feed the samples themselves?
The samples themselves go through.
Okay.
And I'm just thinking about it would have to be the same numbers. The number of samples is equal to your batch size in order for it to go through the decoder as well. So.
Yes, but the input of decoder is by no means.
Yeah, it kind of just disappears after the encoding phase. You're purely relying on this unit Gaussian model distribution, and that's the purpose. Mm-hmm. If that model has sufficiently captured your data, then it should work as if there was no barrier between the encoder and the decoder. If that model works correctly, it should.
Does this mean I train them separately somehow?
No, the weights are, because the loss function is all tying together both the input from the encoder and the output from the decoder, as well as the unit Gaussians. It all has to work harmoniously and together.
So they come as a single block. I work with the whole structure.
Yeah, so when it comes
network.
to building it, you build it all within one sequential model. You don't separate them out. You can, I think in the template, I didn't build a sequential model around it. I should have, just a hint there. But yeah, you should put them all around one one model.
Got it. Thanks.
Okay.
So is there any reason why we want to use the Gaussian distribution instead of the other distributions?
So that exact same question crossed my mind as well. I think unit Gaussians are used because they're generalizable to lots of different applications. I don't think there is a restriction on just using unit Gaussians. The only thing is you would have to adapt your loss function so that it doesn't use KL-divergence, and then what do you replace it with? Because you would have to adapt other parts of your model in order for it to work harmoniously if you change that one function inside it as well. I'm sure there may be scenarios where something else would be appropriate for your data, some other model and function, but actually modifying the rest of the architecture can get quite complex.
Okay.
Yes.
I can ask a question.
Yes, you can.
Yeah, there was one question I had in relation to the slides. So I don't have any experience with variational autoencoders,
Okay.
and I have some experience with information theory and some experience with KL-divergence.
Right.
But in the slides you said that somehow the loss function, the second part of which made use of KL-divergence and like non-normalized KL-divergence, assumed a Gaussian distribution, but I didn't see why that is the case. Because I'm used to using KL-divergence for very non-parametric distributions.
I see. Huh. I don't know if it's just the assumption then that it's unit Gaussians that are used here. So a KL-divergence can be used for other distributions, not just unit Gaussians, is your point.
Yeah,
I did not know that actually.
Okay.
That's something new I learned today. So if you can use it for other distributions, maybe you can substitute.
KL-divergence used in the past in statistics in order to check if distributions are the same. This is the idea behind KL-divergence.
Is there any restrictions on the type of distribution?
How much
any
the
kind of
distribution are the
can
same.
be
This
used.
is the big message of KL-divergence. The reason that they use, for my opinion, a Gaussian, because if there are many Gaussian, you can create a mixer Gaussian model, and with a mixer Gaussian model, you can measure every distribution, not only Gaussian.
I see. Right.
So this is why I think they use the Gaussian.
That's a great point. So the point that was just made was that Gaussians may be used because when you combine multiple Gaussians together, you get a mixture of Gaussians, which can represent pretty much any type of data. And it has that the nice properties associated with Gaussians with it as well. Those are very good points. It might be worth, and I think I might do this actually whilst you guys are all working, looking in the literature and seeing if anyone else has tried any other distributions in the variation autoencoder. I certainly haven't came across one so far, but there might be something out there by someone, and if I do find one, I'll let you know. All right.
And so sorry, again, going back to the previous slide, you
Yes.
have the final layer of the encoder. Is it the case that you're trying to solve for two parameters, mu and sigma, and that you're going to generate samples in accordance with mu and sigma, so that if mu was 100 and sigma was 1, you'd expect numbers centered around 100? You'd expect like
so in this layer
199.
here, the green layer?
Yeah, so
Yeah.
the input would be?
Yeah, the input to the decoder? Yeah, I would assume so, but I think they're...
You kept saying unit Gaussians though, so is there
Yeah.
some restriction there?
There are some restrictions. I was going to say it's between 0 and like -1 to 1, like you have that restriction there.
So, but in this case, are those parameters that get solved? Like, are those parameters in the network that get solved, mu and sigma for each?
Yeah, so
node
they're
gets
trained
solved?
on the way the mean and variance are learned parameters. Yes.
So for each single like edge or node or whatever you want to call it, there's a different mu and sigma
Exactly,
parameter that
yes.
gets solved. And how then does the input layer impact that function?
So the input layer, so when I said the input layer kind of disappeared, that wasn't entirely true. In the loss function itself, it does something very similar to the autoencoder in that it does measure how the output from the decoder, so the output of the entire VE, compares to the input, so the actual raw input that you fed. So in that sense, the loss function is half controlled by your input, as well as the KL-divergence term. So they connect through the training process in that the weights should adjust for your input as well as that unit Gaussian distribution in the middle. So they're not directly connected, but they are indirectly connected through the loss function.
So if I wanted to compute the output of one of the blue edges,
yes,
I would take the inputs from the prior layer and then apply miscellaneous weights to them as per up to the training up until now. And then what would it'd be the activation function as it's defined for the network, and then what? Is it additive sort of noise or what? No, it's a sampling function.
it's a sampling function. So you define a sampling function within your model as well, which samples from that particular distribution.
And does it?
And then that gets fed into the decoder as if it's a new input, like how you would do a new input into the decoder element. So in your Pytorch function, you'll have your X input going into your encoder, then it'll go down to your mean. And then you'll have a sampling function that is called at that stage, which will then generate some sort of Z latent space encoding, and then that Z will be input to your decoder, all within that one train function, I think it's called in Pytorch. And then it ripples through and gives you a reconstructed X, and then your reconstructed X as well as your mean, as well as your variance, as well as your input. So 4 elements will go into your loss function, which we'll also implement today. So you have 4 inputs. And I think in the template, actually, I put those 4 inputs as well. All right. Sorry, any more questions? Okay, we good? All right, if there's no more questions, I want to move on to the practical. So as mentioned, you'll be building a variation autoencoder. I know some of you may not have worked with variation autoencoders, but this is a great way to kind of start off and get into the tune of building models. So there were a couple of questions that were raised. You know, what kind of structure does the variation autoencoder does it need to take? Do you include convolutional layers? Do you just have linear layers? Honestly, I wanted this to be slightly creative in that you have your choice. So I know in my template, and then when I built it up, I flattened out my image and just put hidden layers just to create a really simple 3-layer architecture for the encoder and similarly for the decoder. However, you can absolutely, and if you're comfortable with Pytorch, go ahead, implement some convolutional layers, add some dropout, batch norm, whatever type of layers you like in there. But I would say start off simple and then add them and see how they impact your output. And the default data set I put again in the template was MNIST, but just above that I put a small description and links pointing you to say ECG data and other types of data sets you can use after you get the initial thing up and running. Hopefully you'll implement it in such a way that you can kind of take in and out that data set. Or you can have a string going into that function that says if you ask for MNIST, load in MNIST. If you ask for something else, it'll load in something else. And in Pytorch, if you're not familiar with it, there are data loaders which can automatically augment your data. And so feel free to use those resources. But you can also build your own custom data loaders as well, which is why I gave you the option of other data sets if you're feeling adventurous today. So if you've not used Pytorch at all, there is a tutorial on the Pytorch website called Deep Learning 60-Minute Blitz, and it's one of many, but I find that one particularly nice because it explains absolutely everything that you need for today's exercise. So it has the training and the test functions all in there. So if you're stuck, feel free to use that. You have your TAs on hand. And for today, we're going to be releasing code incrementally. So maybe every, say, half an hour, 20, 30 minutes, we'll release little bits of code. So if you're really, really stuck, you can still kind of get through today's exercise and get something out of it. And we'll release the final version as well after today. So I put a wee note there, why Pytorch? Because I had that question a few times. So because we're working with unsupervised and weakly supervised learning, a lot of the methods we're going to look at are all based on adapting the loss function and adding loss function terms. It's just a lot easier with Pytorch. So I've used TensorFlow, Keras. I even used Theano back in the days. So I've used most of them, and I found this Pytorch is just easier for adapting loss functions and adding terms like that. So that's why Pytorch is there. And so you'll be using Colab for today's exercise. I am well aware that some of you are already familiar with Colab. You might be even, you'll probably know more about Colab than I do. So you have been provided with a template, which I think Ali uploaded onto the Google Share Drive. You can copy it from there, I believe.
Yeah,
Yes?
you need to make a copy to your own Google Drive,
Okay.
which is basically you just go to the file and like in the menu and say like save a copy to my drive or something like that in order to make it editable, because
I
this
see.
version is kind of read-only.
Okay, so if you didn't hear that, make a copy because you won't be able to edit it. So copy the file that's already on the shared file, the shared drive. So I mentioned that you can add convolution layers or dilated layers if you feel like it, whatever you feel like. And the loss function will be the same regardless of what you put inside your model, because eventually, no matter what you put before that, those unit Gaussians, it'll still end up with unit Gaussians. So the loss function will stay the same regardless. And I think that slide is done. Okay, so if you've already started, you've completed it, you already have a variation autoencoder going, there's so many other things you can try. I really wanted you to be able to try beta VE, which was one of the methods that I mentioned during the lecture for creating discriminative features. So give that a go. It's just an added weighted term that's added to your loss function in front of the KL-divergence term. So refer back to the lectures if you don't remember, but it is there. There is a slide on it. In the training function, you'll have obviously your accuracy rates, your loss, as you normally would do when training and testing a deep learning model. But feel free to add additional metrics and you can try visualizing that latent space. A lot of people have done that. And you may use additional dimensionality reduction techniques such as t-SNE to do that and actually show all of the latent space, all the embeddings in the latent space all in one go. You may also choose to use an external libraries. Other people on GitHub have developed visualizations, so feel free to use them. And yeah, get creative and let's see what you can come up with. And with that, I'll let you start your practical session. And we'll check in later.